Now we'll begin with fragmentation. Before that, first of all, we start with a field called total length field. Once we finish it, we'll go to fragmentation. Total length field is having 16 bits. Using that, we are going to mention the size of the datagram. So total length has 16 bits, right? So using that, 0 to 65,535 patterns can be generated. So maximum number is 65,535. So we can measure up to 65,535 bytes. That means the datagrams maximum size can be 65,535, not more than that. But typically, so we don't require more than that. That is what designers finally felt. So we are going to take the data from TCP or UDP, right? Whatever the upper layers. From that we are going to take the data, right? So TCP or UDP generally they don't generate this much size data, so there will not be any problem. We don't get any problem with higher layers. So this is sufficient, I can say, right? That is enough for you. Now we will come to fragmentation. What is fragmentation? I will tell you. First of all, rather than going to these fields, we'll see the problem. Why we have to do fragmentation? So this fragmentation is about your datagram, okay? So network layer creates datagram, we know that, right? In the datagram, this part is header, this part is data, okay? Now such datagram to be attached to, that means that should be encapsulated in another packet, right? That is nothing but frame. We know that. So we are going to give datagram to next layer, that means downside layer, that is data link layer. So that data link layer is going to add extra header, that is data link layer header. We know that. Example, if the technology is Ethernet, we are going to have Ethernet header. So that entire thing will become Ethernet frame. So now let's go to Ethernet. Assume that let's say this is Ethernet. So in Ethernet you have a restriction. That means Ethernet frame can have at most something around 1536 bytes or something. Let's approximately assume that. So Ethernet allows only payload of 1500 bytes. Such kind of restriction we have, right? Recall. That means simply Ethernet technology says that, my dear network layer, I allow only at most 1500 bytes from you, not more than that. Okay, if you give more than that, I cannot accept. So that is called MTU, maximum transportable unit. Okay, so here Ethernet has something like that. Similarly, some other networks also having restriction on maximum data size. So that is called MTU. Whenever you have such restriction, then how to adjust with that, otherwise how to solve that problem, we will see. So finally problem is like this. You have datagram. Assume that for simplicity, it has something around 3000 bytes. Okay, that means entire datagram is 3000 bytes. Assume that in that 20 bytes are header, no options for simplicity. So header size is 20 bytes and 3000 bytes is total datagram. That means including header. Now, this, let's say there is one network through which your datagram has to go. Let's connect the story to this point. Your, here this is host A. Host A is sending 3000 bytes of datagrams through this network to B. So that data should go like this. I will show the flow through network layer. That means at network layer, at network layer level, how data should go, I will tell you. It should start here, then here, then here, then here. That's it. But these two components, otherwise these two routers are part of this network. So when your data is going through this network, definitely these routers will have data link layer, correct? So in that data link layer is having a restriction called 500 bytes. That means they can't allow more than 500 byte. That means at any time. So finally, because of that, these routers allow only at most 500 byte data. But you are having how much? You are having here 3000 bytes. Now problem is reduced to like this. This router allows only 500 bytes data. This router also allows only 500 bytes of data. So that is the maximum allowable unit at downside layer. So then how to solve this problem? That's why, so your host is going to do fragmentation. Okay, for that we will see. It depends. It's not compulsory that host has to do. It depends. Example, let's say host has a problem, then host will do. Some router is having a problem, that means router has a restriction, then that router will do. Finally, so whenever there is a network, if that network has a problem and if your data is going through that network, the nodes in that network are going to do fragmentation. For that, your host should allow it. Sir, how we can restrict ourselves? Otherwise, how can we stop of not doing fragmentation, sir? Yes. For that, here you put don't fragment bit to 1. If this don't fragment bit is 1, so don't fragment is a part of flags. If don't fragment is 1, we so definitely no one will fragment it. That packet will be discarded. Okay. So it is up to you, because you said your packet should not be cut into parts. Then don't fragment is 1. After that, it's up to you, like how you send the data. Then maybe next time you send through other network or anything, but at this moment blindly your routers are going to discard such packets. So finally, R1 and R2 are belongs to some network. That network has a problem. What is that restriction? The network's data link layer has a restriction that it allows only 500 bytes. We try to understand this one. So A is not part of this network, B is not part of this network, but R1 and R2 are part of this network, and your data is going through R1 to R2, let's say. Then how this data will be fragmented, why fragmentation is required, we'll see. First of all, we assume that we have here A has network layer, definitely it will have then data link layer. Okay, similarly physical layer, we ignore physical layer. Now similarly here R1 is also having network layer, data link layer, correct? Now here R2 is also having network layer, data link layer, in that way. So first of all, we talk about network layer of A. So network layer of A is having datagram which is of size 3000 bytes. Okay, directly write values 300 bytes data. For that, we are adding data link layer header. Okay, so let's say assume that this is data link layer header D. So this D 3000 bytes will be sent through this line. So this line is not part of this network. That's why we can send it. Though it is 3000 plus D size, it will come to R1. Whenever it comes to R1, then this header will be removed and this 3000 bytes will be given to R1. Now this R1 is going to send the data to R2 through this line. Remember, this line is part of this network. Okay, this line is not part of this network. That's why. See the circle. So in this network, let's assume that this is, let's say, some Ethernet kind of technology. It is allowing only 500 bytes data at data link level. Okay, now we talk about data link level. Just now this router got 3000 byte data. That means it's easy to see that A and R1 got communicated at network layer level, and this 3000 bytes data got received by R1. Now this 3000 bytes is going to be fragmented. The reason we will see. What if directly R1 blindly send this 3000 bytes as it is, like same like A did? What is going to happen? We'll see. 3000 bytes plus, now here there is a data link layer header. So let's assume that that is D. So D and 3000. Assume that D size something 30 bytes for simplicity. 3030 bytes. Ethernet, I mean, assume that let's say it is some data link layer. So in data link layer now you have 3030 bytes, right? So that 3000 bytes are going to be transferred like this, but it is not allowed here. So there is a condition that these two data link layers are having a restriction that they should have only 500 bytes. That means router 1's data link layer doesn't allow that. So this is impossible at router 1's data link layer. Sir, what if we violate this data link layer rules? Then we should not violate like that, correct? It has this network functionality depends on that one. So that's why finally this 3000 is not allowed here, only 500. That is what this network says. Saying that network allows only 500 bytes means the data link layer at that network, maybe otherwise some physical layer, someone is allowing only 500 bytes of network data. That's it. Now we'll see that. So that's why. But A doesn't know that, right? Simply A sends data 3000 bytes. It will come to router 1. Now it is router 1's responsibility. Now router 1 is having 3000 bytes of data. It is going to do fragmentation. How this fragmentation will be done, we will see. Simple. Because only 500 bytes are allowed. First of all, I will teach you theoretically. Simply divide this 3000 bytes into 500, 500. But be careful, there is a header also. In 3000 bytes, there is a header. That header, should be given to every fragment. Why? I will tell you. Example, let's say you divide fragments like this, fragment 1, fragment 2. Assume that, let's say, you are dividing into 400 byte units. Okay, just for simplicity. So after that, we have to add header also. This 3000 bytes, out of them, let's say 20 bytes is header, right? So 2980 is the data, 20 is the header size of the network layer. So this 20 should be added everywhere. Why? If you don't add 20 bytes header to everyone, how these fragments will reach destination? Because this packet, first of all, before fragmentation, this datagram has header. That header has source address, destination address. That is part of header, right? Please recall. Already I told you, right? Now, if you divide it into some parts, then if only header goes to one of the fragment, not to others, then how other fragments will reach the destination? That's why we have to divide only data part of the network layer. Remember it. Okay, that is one thing. Now we'll see clearly how this fragmentation will be done. For safe fragmentation, because there will be a lot of problems if you don't do properly. That's why we are going to use identification number. We'll see one by one. Identification bits, and there is a fragment offset, and flag bits. We are going to use all these things. First of all, we'll see flag bits. Flag bits are three. One is don't fragment, second one more fragments, third bit unused. That means you don't use this third bit. Okay, ignore about it. That is not defined. So don't fragment, more fragments should be defined. So what is don't fragment and what is the bit pattern we should use? There are two possibilities, 1 and 0. It depends on route, your initial source. If source doesn't want this fragmentation process, maybe we don't know the reasons. Okay, so finally A doesn't like this fragmentation because it knows that the receiver is not capable of I can say merging them back. Okay, so that is defragmentation. So A will not allow it. That's why don't fragment bit is 1, because sender knows the receiver's capability. Receiver cannot do defragmentation. That's why don't fragment will be 1. If your sender knows that, let's say, we can do fragmentation because this receiver also knows about this fragmentation, so this will be 0. That's it. Now more fragments. Why more fragments? I will tell you. How this receiver, we will slowly understand more fragments. You see, once you do fragmentation, example, let's say these are all fragments of your datagram, I can say. This is fragment 1, fragment 2, fragment 3, fragment 4. For fragment number 1, we are going to keep more fragment bit 1. That means there are more fragments. Second fragment also more fragment 1, third fragment also more fragment 1. For last one, we keep more fragment 0, so that receiver will understand how many fragments are there in overall and how to merge them. Okay, we'll see how this data, that means this more fragment, will be used by your receiver. Okay, remember that receiver is going to use this more fragment bit. Now one more thing, fragment offset. Now we'll see what is fragment offset. So how to understand fragment offset, I will tell you. Actually, the designers gave 13 bits to it. So fragment offset is going to represent the byte position, otherwise the starting byte number of that fragment. Example, let's say you have some 8000 bytes of data, okay, in your datagram, especially in the data part. You have header also. Apart from header, you have 8000 bytes of data, which we are going to divide into, let's say, some two parts. Okay, something 4000. We'll see the reason for that. Why 4000, 4000? At this moment it is inappropriate for us. But what if you divide it into 4000, 4000? You can divide 3000, 5000 also. Okay. So first of all, try to understand the concept of this fragment offset. If you divide 4000, 4000, then what is going to be fragment offset? I'm going to tell you. So 8000 bytes you have initially, I can represent that all that bytes with numbers, right? Just if I want to logically represent, I can say byte 0, byte 1, byte 2, up to 7999 byte, correct? So if I divide that into two parts, 0 to up to 2000, what is the division? 4000 each, right? So 0 to 3999 bytes are going to come here. 4000 to 7999 are going to come here. So here fragment offset is nothing but the first byte. 0th byte is here, first byte. In the first byte of second offset is 4000. In that way, so 0 and 4000 are going to represent the fragment offset. Okay, that is important. Using that only, your receiver can defragment properly. Okay, first of all, let me define this fragment offset. We will see how to use it. So the relative position, of course. So the data and its relative position is important for again merging it, right? Example, let's say you are dividing in, something. Forget about these networks. Let's say you have something, a book. You are dividing into three parts, but order is important for you. Then how you divide? How you remember it that this is first piece, this is second piece, this is third piece, right? So for that we are going to use fragment offset. Example, let's say your book has 100 pages. You write like this. This is 0th page. That means this fragment is having 0th page first. Now here you write 65. Then here you write 79. Example, if you write like that, then how people can understand at receiver side? Oh, 0 means this is definitely first fragment. Now 65, 79. So definitely it must be 65 should be the second fragment. So 79 will be third fragment. In that way they will understand. Okay. So this is about fragment offset. Now we'll see some other details about fragment offset while defragmentation at this moment. So we'll see one more problem with the fragment offset, that is limited number of bits. We have only 13 bits. Sometimes 13 bits are not sufficient. Why, we will see. Example, what is the maximum data you can have in datagram? We know that total datagram size is 65,536, right, at most. Correct? So if you have 65,530, of course, there is some header also. Header will occupy 20 to 60 bytes. Approximately, I can say, some 64,000. More than that, of course. Let's take one rough idea that, let's say you have data size 64,000. Then, see the problem. And you are doing the fragmentation. If you do fragmentation, and each fragment is having very small size, 1 byte. If you allow it, what is going to happen, we'll see. Then what is the fragment offset for this one? 0. What is the fragment offset for this one? Because it's a first byte. Now each fragment is having only 1 byte. Then your next fragment offset will be 2. Correct? This is the second byte, starting byte. So what is the starting byte in this fragment? 3. In that way, the last fragment number will be 64,000 minus 1. That means 63,999. Now here interesting question is, to represent this number, where we represent this fragment offset? In our header, right? So in every fragment there will be header. We are going to add it. Like your initial data has a header, for every fragment, once you do the fragmentation of your data, we are going to add the header. That header is going to have fragment offset bits. How many? 13 bits. Remember one thing, there is no difference between your fragment and your original datagram. Original datagram will have header, right? Similarly, every fragment will have same set of, same structure of header. Okay, remember it. So in that we are going to write offset. How many bits are required to write offset which represents 63,999? Remember one thing, to represent 7 in binary format, 3 bits are required. Correct? So to represent 8 you require 4 bits. That means I can say log 8 base 2 plus 1. Correct? So approximately, forget about that exact value, we don't require exact value, but approximately I can say log that the number, right? If you want to represent any number in binary, then that number of bits required equal to log n, where n is the number. Similarly, this 63,999 is going to be someone's offset. We want to represent it. For that, we are going to use log how many bits? 63,999 bits if you want to represent it binary. So that is going to be approximately, if you simplify it, something around 15 bits to 16 bits. Okay, so you require approximately 16 bits, but we have only 13 bits. With 13 bits, what is the maximum number you can write is 8,191. Remember it, with 13 bits. So, but we have to represent 63,999. How you do it? That's why they put a condition. Simple. So every fragment should have minimum size. That means, the fragmentable unit should be 8 bytes. That means either you can have one 8 byte or two 8 bytes or 3 8 bytes in that way. In simple words, I will tell you, every fragment should have this kind of sizes. 8 byte, your fragment size should be otherwise 16 bytes or 24 bytes or so on. If that is the case, then we can represent that sizes with 13 bits. We will see that why. Now we'll see an example. So there is a datagram of size 100 bytes. Whenever I say datagram, that covers network header also, right? So network header, let's say NH is 20 bytes for simplicity. So remaining 80 bytes are your data, which is given by transport layer. Doesn't matter for us. Now your data link layer has a restriction. Data link layer is having maximum transferable unit, so that is something 40 bytes for simplicity. We'll assume like that. That means it allow only 40 bytes of data in payload. So how to imagine data link layer structure? Data link layer will have header, correct, followed by payload, right? Here this we can write the data. So this payload is nothing but this one, 100 bytes, correct? So payload allows datagrams, but what is the size? It is restricted to 40 bytes. Now you have to create only 40 byte datagrams, but you have now 100 byte datagram, 80 bytes data, 20 bytes network header. Now we have to fix here only 40 bytes. Then we do fragmentation. How to do fragmentation? I will tell you. Remember one thing. I am now skipping this data link layer part. Data link layer simply said that if you give me 40 bytes, I can send. That's it. So now we can forget about the data link layer discussion, unnecessary. Our problem is now network layer problem. In network layer, we are going to do fragmentation. We are going to give suitable datagrams to data link layer. For that, how we are going to divide our datagram into multiple parts, we'll see. Only the number is important. What is that? The data link layer said 40 byte data you have to supply. Now this 100 bytes should be divided into how many parts, we will see. One possibility. But you remember one thing, how many fragments you do doesn't matter. In each fragment, this 20 bytes has to be copied, because that is network header, which is important. Now remaining thing is how much? We have overall 100 bytes. Out of the 20 bytes is the header. The remaining data 80 bytes. That 80 bytes should be divided into fragments. The first fragment can have 30. Is it possible? 30 plus 20, 50, but only 40 is allowed at data link layer. For data link layer, this entire thing is payload, correct? Datagram. So here I am creating the datagram which is suitable to this one. Let's have 20 here, 20 here. Just one of the possibility. Still how much data we have? 80 bytes. 20, 20 gone. Then still 40. Then 20, 20, 20, 20. See, this 20 is network header, but we are copying 4 times. Remaining things, if you see 20, 20, 40, 60, 80. So 80 bytes data, 20 bytes network header. Finally 100 bytes is divided. This is fragmentation. Okay, understand the process. Sir, I have a doubt. What is that? 20, 20, 40 plus 40, 60, 80, 120, 160. Sir, you are creating 160 bytes. Yes, but out of that, this 20 bytes, 20 bytes, 20 bytes, all are same. Correct? If you remove that 320 bytes which are duplicates, then effectively how much data we are creating? 160 minus 40, 40, 80, 120, 160, right? So out of 160, so this 20, 20, 20 will be redundant. Let's remove it. 160 minus 60, 100. Effectively only 100 bytes valid data you have. Yes, initially we have 100 bytes valid data, correct? It's matching. Now one more thing. But here fragment offset should be divisible by 8. Already we discussed it, right? Blindly remember it. So if you see here, if you divide into 20 byte data units, then fragment offset cannot be divisible by 8. Example, you see 0 to 19, correct? It is 19 to, what is the fragment offset? 19 to, I am talking about data part, 0 to 19, here 20 to 39, 40 to 59, in that way. So this 20, this 40, of course 40 is divisible, but 20 is not divisible by 8. That's why this is not the proper fragmentation. For proper fragmentation, that's why what we are going to do is, I will tell you. Now let's remember the story. Datagram, having now 100 bytes. Out of that, header is 20, 80 is now data. Okay, this is data, this is header. This entire thing is payload. For whom? Data link layer. So what data link layer said, I want only 40 bytes data. So this 20 is compulsory. Now we are doing fragmentation. Network layer do fragmentation like this. it will add 20 first, then it will think about remaining thing. 40 minus 20, 20. But 20 is not divisible by 8. So we have to always have 8 byte units. How many 8 byte units we can have? 1 8 or 2 8s or 3 8s. So 3 8s are 24 we can have. If I use 24 bytes here, 24 plus 20, 44, but it is more than 40. So we can have next smaller number, which is nothing but 16, correct? 16 plus 20, 36, which is smaller than 40. Very good. Now remember one thing, this 20 is this one, remaining 80 should be represented. So 16, 16, 16, 16 and 16. How many fragments we are going to create? 1, 2, 3, 4, 5. 16 5 is 80 matching. This 20 is nothing but network header. Now see, this is going to be payload for data link layer. How much? 16 plus 20, 36. What it said? 40. Yes, pretty cool, correct? So finally, this is fragmentation. Now we'll see the fragment offsets for everything. For this fragment, offset is, simply see this data bytes, 0 to 15, correct? So 0 is the first fragment offset. Now second one, it is 16 to something. But already I told you, we have to divide that 16 by 8. Whatever the resultant number you get, that only we should write in the fragment offset, because we are capable of only that. So 16 by 2 is what? 16 by 8 is 2. Then this fragment offset will be 2. Okay, in binary of course. Now what is the fragment offset for this one? We'll be writing like this. We have 13 bits, right? I don't show all that 13 bits, but last bit I'll show 0. Okay. Now in this one, what is fragment offset? 1 0. Now here 16 plus 16, 32, right? So the next byte is starting with 32 number. So 32 is represented by 32 by 8, which is nothing but 4. So it would become 4. So here fragment offset is 4. Now here, if you want to know the fragment offset, 16 plus 16, 32, 32 plus 16, 48. So 48th byte is going to here, right? So 48 by 8 is 6. In that way, easily we can guess that this is 0, 2, 4, 6. It would be 8. So in that way we can find out the fragment offset. So the formula for fragment offset, you just write out. Okay, what would be the formula for fragment offset? Simple. First of all, we have to count the size of the data before this fragment. So if you see that, it would be 16 plus 16, 32, right? Example, let me talk about this one. 16, 16, 32, 48, 54, 60. You have 60 bytes of data before your fragment. That's why this fragment offset will be 60, correct? 16, 16, 32, 48, 64, this one. So 64 bytes of data is already there before your fragment. So this fragment starts with 64th byte. So if you divide it by 8, you are going to get fragment offset. In that way we can easily find out. Not a problem. So this is about fragment offset. Okay. Now you understood slowly that how to divide the data into fragments. Now we'll see one numerical example and we try to fill all these values so that you can understand each and everything clearly. And before going to that, one more thing we have to see, what is identification bits. So the identification bits are usually typically 16 bits, correct? So why this 16-bit identification number is required? Since you are going to divide your fragment into your datagram into multiple fragments, right? So that fragments all should have some unique number. Otherwise what happens, I will tell you. Example, consider this situation. You have datagram. Because of the restrictions, you divided that datagram into fragments. Fragment 1, fragment 2, fragment 3. So eventually they will be arriving to destination. This is the destination. So at destination, F1, F2, F3 comes. Question number 1. How do you know that all these fragments belongs to same datagram? That is a question, correct? So that's why to uniquely identify that all these fragments belongs to same datagram, we have to give same identification number to them. That's why the designers decided to have identification number in original datagram. Example, while creating the datagram itself, one identification number will be created. Example, let's say there is a datagram, its identification number is 7. Then when fragmentation takes place, then that whoever fragments it, any router can fragment it, correct? Then he is going to keep this identification number as 777. Understand? So this is the way we use this identification bit. Now when all these fragments comes to this destination, So how destination is going to defragment, we'll see. So he will first of all collect all the fragments with same identification number. So we can say that these are all part of same datagram. Second thing, what is the first fragment? If you want to know the first fragment, then we go with fragment offset 0. We identify a fragment whose fragment offset is 0. That is the first fragment. Then after that, in that way, simply sort them. Take all the fragments and see the fragment offset bit, and you write them in sorted order, because you remember one thing, whenever fragmentation is done, then that fragment offsets will be they will be in increasing order, correct? So based on their increasing order, we can find out that this is fragment 1, this is fragment 2, this is fragment 3, correct? That is done. Now this identification number tells that these are all belongs to same datagram. Otherwise what happens, imagine there are two datagrams, but you don't write identification number, don't keep that field in your IP header. If there is no such field, what is going to happen is, for you as a human being, you know that this is datagram 1, this is datagram 2, but when these two datagrams comes, before that, let's say this datagram is divided into 3 fragments, another datagram is also divided into 3 datagrams. But as a human being, again you know that this is part of datagram 2, this fragmentation is for datagram 1, then all this comes to here. Then how do you know that these 3 belongs to one datagram, these 3 belongs to another datagram? There is a confusion, there is a chance that you mistakenly assume this fragment for this fragment, correct? There is a chance. That's why, to avoid that, it's very simple. Every fragment, or sorry, every datagram should have one unique identification number, that is identification number. Generally it will be 16-bit one. Then you remember what, how many identification numbers we can generate? 2 to the power of 16. Okay, remember it. So after that, we have to wrap around. That means once any network layer generates 2 to the power of 16 identification numbers, after that it has to repeat the previous numbers. But by that time, so all these datagrams would have been reached your destination. There will not be any collision, I will tell you. Example, this is your network layer. So it is creating the datagrams, right? So it will be like this. This is a datagram. It will be data part which is given by your TCP layer or DUDP. This is your header, right? In this header, we are at network layer. So I am talking about IP protocol. In IP protocol, you have IP header. So this IP header is going to have a field called identification number. We are talking about that identification number. The size is 16 bits. So the question is, first datagram gets what? Example, let's say in the early morning, when your IP layer started sending the datagrams, this is datagram 1, this is datagram 2, in that way it is creating the datagrams and it is sending. When D1 is created, then some identification number should be given for that. Assume that, let's say 0 is given. So if you come in ascending order, it will be systematic. Then 1, then 2. Then after some time, so your network layer is going to create a packet, its index is, let's say, 65,536. Okay, now we can give what? 65,535 as identification number. With 16 bits we can represent it. But now problem comes. You have next packet which is 65,537th packet. For that, what is the identification number we have to give? So that identification number should be one of them, because according to PG&OL principle, we can generate only 0 to 65,535. We can't generate the next number 65,536 because that won't fit in 16 bits. Then we have to repeat the previous bits. Let's repeat again 0. Then only question comes, sir, there is a, like example, let's say receiver gets this D65,537 and receiver gets D1. Since identification number is same, okay, now this D1 is divided into some 3 fragments, F1, F2, F3, and this D65,537 also divided into 3 fragments. Then there is a chance that receiver might get confused between this F2 and this F2, isn't it? Because sequence numbers are same, identification numbers. How these two can be differentiated? They have same structure, correct? Same IP address, same destination IP address, right? Same protocol, everything is same. There is a chance. Now to avoid that, and why we don't need to avoid, I will tell you. To understand that this is a very rare phenomena, you never get this kind of problem. Why this problem is not a big problem, I will tell you. Assume that, let's say, your network layer is taking 1 second to create one datagram. Okay, it's reasonable, right? So your network layer is creating one datagram for 1 second. Then how long it will take to create these many packets, we will see. So when you get a problem while creating this packet, right, let's say early morning you started at time 0, t equal to 0, and you started creating datagrams. To create one datagram, 1 second, second datagram, one more second. Now the clash comes when you create d1 and d65537, right? So by that time, how much time it will take, we'll see first. Since you have 16 bits, with 16 bits, 2 to the power of 16, which is nothing but 65,536. After creating 65,536, up to this point there is no problem. So 65,536 datagrams creation takes 65,536 seconds. If I convert that into minutes, it would become 65,536 by 60. So I can say 6,553 by approximately 6. So it will take 6 6 tens are 60, 5, 55, 6 nines are 54, 13, 1092 point something. So minutes, right? If I convert them into hours, divide by 60 seconds again. So approximately, I am approximating every time. So 6, approximately it would be 16 hours. So you are going to use same identification number 2 times, I agree, but after 16 hours. 0 and 0 will be repeated after 16 hours. But you remember one thing, already I told you we have a field called time to live. So your fragments or datagrams are going to live only for some 10 seconds, otherwise at most there will be some fixed number. So 1 minute at most, not more than that. So no one keeps the old packets for 16 hours time, right? So because of the time to live, the typically time to live, because of the time to live, so every datagram is going to stay in an internet only for 1 or 2 minutes, not more than that, because it is unnecessary to keep it, right? Before that itself, really there is a destination will take it. Now no one, we never wait for 16 hours, then there is a danger, there is no way we can repeat the numbers. When by this time, when you create this kind of datagram with same 0, by that time this would have been reached, so there will not be any problem. Understand? So this duration is very long. We are creating a huge patterns, right? So that when one pattern matches with another, another pattern only after 16 hours, but no two packets will stay that much duration, right? So that's why there will not be any problem. You remember it. Okay, so here some numerical questions they can ask. They ask, what is the wrap around here? That means, example, let's say some network layer is creating one packet for 1 second. Then when will you be going to repeat the sequence number again? After approximately 16 hours. It's not exact calculation, but you should do exact calculation. Just I did a rough approximation to just explain the problem, that's it. But you understood the procedure, how I am doing. Second thing, now we'll see fragmentation clearly. That means we take one numerical example and we'll see how to do fragmentation and what will be the fragment bit, most fragment bit in all the patterns, and what will be this fragment offset, everything. In the GATE exam, they will give you a problem and they ask what is the fragment offset and how many fragments has been created, everything. So if you know the fragmentation way, that means how to do it, you can answer it, not a problem. We will see that. Now we'll see one numerical problem related to fragmentation. Assume that, let's say, you have datagrams of size 1000 plus 30. You have only one datagram. 30 is header and 1000 is data which is coming from transport layer. So this entire thing is what? Datagram. Remember it. And that 30 is the header, 1000 is data part. Now such datagram has to be transferred from sender to receiver. But the problem is, it is going through some network. That network has 250 byte limitation. That means this network says that, especially the data link layer of this network says that I allow payload of only 250 bytes. It's like, it's telling that like this. This is your network. Network is having 3 layers, correct? Now this is the communication between these two. Network layer, data link layer. Now see, they are talking like this. Sender sent some datagram. Now network layer received it already. Okay, so now we'll see this network layer is having, let's say, A, correct? So now A is received a datagram which is like this 1000 and 1000, 30 and 1000. Now it is communicating with data link layer. My dear data link layer, now this is the time to transfer that 30 plus 1000 units of data to another place through this network. Please allow. Then the data link layer says that you can't give me 1030. This payload I can't take because I can take only payload of 250 bytes. So now this A's network layer is going to do fragmentation. Okay, simply remember one thing. Now every network will have some limitation like this MTU. That MTU is decided by data link layer 250. That means by seeing this 250 you should understand that. So your datagram size should be only 250, but you have 1000 plus 30. What to do then? We have to make suitable size things. Okay, for that how fragmentation takes place we'll see. Now we are doing fragmentation because of this network. So A is, let's say router A is doing fragmentation. Okay, the first packet how it will keep we'll see. Okay, so fragment number 1, what is the size? 250, right? But on that network header is compulsory 30 plus remaining data how much we can keep? Only 220. Now 220 is actually a problem. Why? Already I told you the data how much whatever you are taking, that should be divisible by 8, then only we can write fragment offset properly, right? We have a fragment offset bit. For that your fragment size should be, this is I can say fragment size, this should be divisible by 8, especially the data part. So 220 divided by 8, try it. First of all 8 to the 16, 60, 27.5. So it is not divisible. Then what to do? That take 27 and multiply with 8. You understand now. 8 7 is 56, 5, 8 2 is 16, 16 plus 5, 21, 216. So we are going to keep 216 bytes only. Okay, don't worry. But how much data we have? Remember 1000. 1000 should be finally completed. So how many fragments we create? I will tell you. One is 216. Second one 216. 216 plus 30, 246. Is it not allowed? Yes, 250 is maximum. So 216, 30. Second fragment. Another fragment 216, 30. In that way. How many fragments we have to create approximately? I will tell you. 1000 should be consumed. So 1000 by, because every fragment is of units 216. So 1000 by 216 is how much approximately? 216 5s, correct? So if you divide only 4 fragments, then 216 4s are 864, but we have 1000, right? So first we create 4 fragments because 1000 by 216 is 4, but that is not sufficient, I know, but let me do that first. Then how much data is consumed? We'll see. 216 into 4, correct? 216 into 4 is 864. Okay, so out of 1000, 864 is already represented. Then remaining thing is what? So 36, right? 136. So that 136 will go to the last fragment. That's why every fragment may not have same size. Last fragment may have different size. Remember it. Okay. Now again the network header is 30. In that way your router here, that means network layer of A is going to do fragmentation like this. Now each fragment will be given to the data link layer. So data link layer will allow it because it is allowing 250 bytes. Now we will see these bits for every fragment. First of all, focus on only one fragment. What is the identification number? So identification number represents uniquely a fragment, a datagram, right? This datagram is divided into these many parts. Every datagram should be represented with same identification number. That's why in this header we are going to write identification number as 25. Remember it, ID 25. Now here also 25 because all are part of same datagram. In that way uniquely we represent them. Second thing, ID is done. Now what else? Don't fragment bit. So since fragmentation is allowed, already we know that, that's why we did fragmentation. So don't fragment. See, everywhere there is a header. Remember, already I told you IP4 header, right? IP4 header will have version, protocol, everything. So we will definitely have don't fragment bit in every header. So where we have to write? Yes, don't fragment is 0. That means further fragmentation is allowed. Okay, in that way. Next, fragment offset. This is important. How fragment offset will be fixed? If you see, this is first fragment, right? In that write simply 0. Now second fragment. Second fragment starts with 2/16th byte. 216 by 32. If you simplify, you get 27. So first offset will be, second offset will be 27. After that this one. So far 216 plus 216, 432 bytes are gone. Then this offset will be 432nd byte, right? So you divide by 8, it will be 8 5s are 40, then 32, 54, right? 27 to the 54. So easily we can understand now. 0, 0 plus 27, 27, 27 plus 27, 54, 54 plus 27, it will be 81, 81 plus 27, right? Because every fragment is consuming this 216 bytes. That's why offset will be moved by 27. 81 plus 7, 88 plus 27, 108. So this will be the last offset. So finally we calculated offsets. All these fragments are now happily will be traveling through this network. But remember one thing, once they come to this router, which is last router in this network, then let's number them. Fragment 1, fragment 2, fragment 3. How many fragments we prepared finally? 1, 2, 3, 4, 5. All these fragments will take different routes and they will come to this router. It is again, they are like datagrams. How datagrams will go? They will go depends on the router which decides it, correct? So here example, this router decides to send one like this, maybe two like this. Example, there is an intermediate router here. Okay, then this is one path, there is another path. Some of the fragments may go like this, some of the fragments will go like this anywhere. So finally they are independent units, they can be forwarded like anything. Eventually they will come to this end of the router. Now what I want to tell you is, once this kind of network is passed, then defragmentation will not be done at this moment. Sir, we did not understand. I will tell you. See, so far finally this network is closed, right? That means we completely travel this network. We are coming out of this network. At that time, should we, merge all the fragments? No, we don't do. Reason number one, why we don't do? Because this router, let's say if this router is doing defragmentation, which is the last router in this network, then problem number one this router is going to face. So it doesn't know when they are going to come, right? It unnecessarily makes the things slow, right? First of all, to do defragmentation, all the fragments should come to this router. For that, unnecessarily that router has to buffer them. So what can happen? One fragment may come very fast, and another fragment comes very slow. Then by that time, so up to that time, all the fragments has to be buffered, correct? We have to wait for the last fragment. That is the problem. Second thing, once you do fragmentation after a lot of effort, then what if you have another network through which you have to go for reaching the destination? This network has again restriction like same 250 bytes. Then again we have to do fragmentation. To avoid that, so you should be very lazy. There are two major problems. One is unnecessarily it takes lot of time to do the defragmentation at router, because router has to collect all the fragments, and for that it has to, all the fragments has to wait. Now see, you're stopping the speed, correct, or progress. Example, see the story. One fragment has already arrived. If you don't do defragmentation, if you simply send that fragment, happily it will go and it will reach destination. But here what you are doing is, you are unnecessarily we are stopping fragment number one. That fragment number one has to wait for others, so that unnecessarily everyone is, I can say everyone is just stopped, right? That is a problem. To avoid that, generally we don't do defragmentation at intermediate routers. When will we do defragmentation? That is finishing touch, in the climax, when all that fragments will receive to destination. That destination's network layer is going to do defragmentation using all these helping bits, identification number, this more fragments bit and fragment offset. And one more thing, we did not discuss what is more fragment, right? Simple. So here, what is more fragment bit, I will show here. For first one, we'll ask Mr. Fragment number 1, do we have any other fragments which are related to you? Yes, that means there are more fragments. Similarly, do we have any other fragments after this one? Yes, more fragment bit will become 1. So in that way, every fragment except the last fragment will have more fragment bit is 0. That's it. Okay. So finally, you understood how to find out the number of fragments. Second thing, what are these bit patterns and everything, right? Now one more thing, sir, what if there is another network whose size is just 125 bytes? That means it allows only 125 bytes. Then forget about previous fragmentation. Assume that these are all now again datagrams. When given a datagram, when you have a problem like this, how you divide? In the same way blindly we divide, not a problem. We'll take one more example where there are two networks, I mean having this kind of two restrictions, then how to send through that kind of networks we will see with another problem. At this moment we have only one network. Okay. Now we'll see one more example and see fragmentation. So datagram is having 1000 data bytes and 20 header bytes. Okay, this is network layer header. Okay, network header version, offset, everything, right? So IP version 4 header. So this is this one. That means options are 0. Now sender is sending this kind of datagrams. They will go like this. So here when they are passing through this network, so only 500 bytes is allowed. When they are passing through this one, 250 bytes are allowed. Then what we are going to do, we'll see. So first of all, we have 1000 plus 20, 1020, right? Now here what we do is, first of all we'll ask what is your allowed rate? Only 500 bytes. Then however we have to keep header guaranteedly, right? That's why keep 20. So still how, because this says that datagram size 500, but we have 1020. So for 500 network header is compulsory in the datagram. Then what else we have to keep? Only 480 maximum. 480 plus 20, 500. See, we are satisfying. That's why what we do is we keep 20 header and only 480 data. Correct? Second thing, how many such things we should do? Before that, we should see this 480 should be divisible by 8. Is it true? 8. 8 6 is 48, 8 60 is 4080, correct? So now there is no problem, remember it, that is necessary condition. Now take one more fragment, on that you write remaining 480. Now we have only 1000 bytes of data, right? So 480 plus 480 is 960, remaining 40 we should write here. 20 plus 20. Remember one thing, for this one, this 40 need not be divisible by 8. Of course, 40 is divisible by 8, but this, whatever the remaining data may not be divisible by 8. That is not compulsory, because based on this we are not writing offset. We are writing offset based on these values. That's why these values should be divisible by 8. Okay, you will get it by experience. Now, so this is the fragments. Let's say fragment 1, fragment 2, fragment 3. Okay, now more fragment bits in every header, right? So more fragments are 1 1 0. Now identification numbers. Example, let's say this datagram's identification number is 27. Just for one example. Okay. So ID is 27. Here also ID will be 27. ID will be 27. ID will be 27. Okay. So that's why I don't write it, because that's obvious that every header will have 27 as identification number. Okay. Anything else? Only offsets we have to see. What is the offset here? Simple. 480 by 8, 60. So this is 0 offset, and here offset is 60, because the first byte is 480th byte, correct? 480s. With respect to 8 units, it will be 60. Now here it would be 480 plus 480, 960, but you have to divide by 8. So you get 120. So 120 will be the offset. It's quite easy. How to calculate offset? First of all, directly write 0. For this one, take this one and divide by 8. For this one, take these two units, add them and divide by 8. That's it. So in that way we get offsets. Now these three fragments are going happily through this network F1, F2, F3. Now they come to here F1, F2, F3. We don't have any problem. Treat them like independent units. Then do fragmentation again. So now problem is reduced to, I show only for this fragment. So similarly you can do for this one. We have, let's say, fragment number 1, which is arrived first. That is having like this 20 units of header, 480 units of header. Now we are at network layer. Now this MTU, this data link layer says that if you want to send the data through data link level, that means through this medium. So the condition of data link layer is what? 250 bytes size, correct? That means finally remember blindly, your datagram should have only 250 bytes. We have 500 bytes now, correct? Then what to do? Simple, fragmentation. How fragmentation will done, we'll see. First of all, take the network header, copy it, 20. Still how much is allowed? 250 minus 20, 230. But 230 is not divisible by 8, but remaining that 230 should be divisible by 8, then only we can keep 230 here. First of all, try to divide it. 8 to the 16. 70, 8 8 is 64, 28 point something. So we take only 28 units. That means 28 8 is a 8 6 is the 64 6, 8 2 is the 16, 224. That means so 224 units we keep so that that number will be divisible by 8. After that 20 again 224. Be careful how much data we have, 480. Out of 480, so definitely if I divide 240 happily, I can have two packets, but I am dividing 224, then one more fragment we require 20. In this one, how much data we have to keep? 480 minus how much is gone? 448 is gone. Then remaining thing is what? 48, 80 minus 48 is 32, I think, right? So 32 bytes. Now we will see only two things. What is the identification number in every network header? Simple. Identification number is same thing. What was the old identification number that will be copied? 27, 27, 27. Fine. So more fragment bits will be for this one. More fragment. Yes, more fragment is 1. More fragment is 1. This is 0. Just think independently. What is the meaning of more fragment? That means do we have any other fragments? Yes. After this one there is another fragment. After this one there is another fragment in these three. So 1 1 0. Anything else? One more is we have to bother offset, right? What is the offset? Simple. First of all, offset 0. Second one, take 224 and divide by 8. You get what? 224 by 8. 8 to the 16, 28. So next one, this one. 224, 224. 448. Divide by 8. 8 5 is a 40. 40 and 56. You get 56. These are the fragment offsets. Understand? Now, these packets are happily going like this. Now similarly, this frame will come, this datagram will come, again that will be divided in the same way. This packet will come, that will be again divided like same way. Okay, but here division is not required because how much data you have? 40 plus 20, 60 only, but it allows 250 bytes. There will not be any problem for this one. Now in the GATE exam they ask how many fragments are finally going to arrive at receiver. I will tell you. First of all, fragment 1, 2, 3. These three fragments will come here. This fragment will be further divided into three parts. Note down it. Now this fragment also will be in the same way because size is same, right? Then same way three fragments it is going to generate. After that, this will happily move around this network. There will not be any problem. It will not be further fragmented, only one. So I can say that 3 plus 3 6 plus 1 7. 7 fragments will be created overall. That means end of the day, how many fragments are going to come? 3 from this, 3 from this, 1 from this one. 7 fragments. This kind of questions they ask. Okay, now we'll see the last point, that is, sir, once all the fragments comes to destination, how receiver is going to defragment them? That means how it is going to merge them? Very simple. First of all, it will collect all the fragments with same sequence number, that means same identification number. Okay, but still there is a chance that F1, example, let's say these are the fragments which are created, right? F4, F5, F6, F7, 7 fragments. What if one of the fragment is lost in the communication? So how this receiver is going to find out? Simple. Example, this is fragment 1, right? Fragment 2 is missing. Then fragment 1 will have the, in that header, we have the size of this data. Remember it. Okay. So based on that, easily we can decide, is it the F3 is the second fragment or third fragment? It's quite easy. Okay. You also think about it. Now we are going to have this fragment size. Based on that, this offset will be decided, right? Because this offset says that how many bytes are there in the previous fragment. So based on that, easily we can check whether F3 is the second fragment or not. Okay, now I'm just giving the hint. You have to think about it. Every fragment will have network header, right? IP header. And that there is a length field. And that length field mentions size of each fragment. So this fragment's length will be given in this fragment. This fragment's length will be given in this one. Now if something is missing in between, example, you have only this fragment and this fragment, then definitely easily we can recalculate the fragment offsets. I will tell you. Example, I know that there are 224 bytes in the first fragment. Then the next fragment's offset should be 28. If it is missing, if I see directly 58, I can easily understand that some fragment is missing. In that way, we will find out. Okay.